Cool. Okay, awesome. Thanks for bearing with the technical difficulties. I'm dmarz, excited to be here at Sequencing Day. I was gonna make a joke that I don't know the difference between a sequencer and a block builder, but I think Ed's last talk just clarified a lot. Cool, so I'm gonna be talking about supercharging sequencers with TEEs and how that can basically give stronger preconf promises, which we'll get to at the end. So some quick notes. Sequencer, in this talk, sequencer will equal block builder. I think there's like a world where block builders, where rollups have like external block builders, but for this talk, I'm going to avoid that. Additionally, when I mention interop, I am referring to optimism style interoperability protocols. There's a bunch of other ones. IBC is like the most used example, but I won't go into that one. And then another quick disclaimer, we're TE and cryptography optimists of Flashbots. We have a bunch of TE products. We have a block builder on mainnet that's running multiple different versions of TEs. We have a test net in the latest generation of TE software. And additionally, we've peered into the soul of FHE and MPC, and we're excited, but not for a few more years. Cool, so the rough outline of this talk is we'll do like a very brief TE intro. I'll then make a claim that TEs provide defense in depth for privacy, security, and then the sort of like newer, more controversial claim is that it also provides defense in depth for cooperation. Last, I'll set the stage of roll-up interop, specifically with the OP interop protocol, and then I'll say talk about why interop needs preconfs. Cool. So let's get into it. The simplest mental model for what a TE is so it stands for a trusted execution environment. It is essentially just a secure computer you're running in someone else's computer. Very overly simplified, but that's how you can think of it. You can basically encrypt things into this secure computer. It has a hardware-based private key that you can encrypt to. It will then decrypt whatever's coming in, process it, execute it, do whatever, and then send it out. So it's important to talk about the motivations for why TEs have come around. In the academic literature, the closest thing is like sandboxing, which is a very broad concept, but the idea that you want to like isolate execution and data from other processes and people. And then in the industry, the reason TEs have popped up is that cloud providers offer like a range of services, compute, storage, they allow you to flexibly scale these things and all that, but for a while they offered no guarantees for privacy. You sort of just had to trust them, or maybe in the extreme case, they would take all your computers and put them in a different warehouse protected by guys with guns. So yeah, so this started as an experimentation in, well, it started being successfully experimented with in industry by a lot of cloud providers. As I previously went over, trust execution environments, hardware-based security technology that protects sensitive data and applications from a malicious host or hypervisor. And there's like three real components to them: segregated area of memory and CPU, there's a hardware secured private key, and then lastly, there's an attestation protocol, which I think is like one of the coolest and most underrated parts of TEs. Yeah, this attestation mechanism, it's used to ensure the authenticity of the hardware and as well the correctness of the application running on top of it. So if you're talking with a TE, you get some type of guarantee or signature from someone that the code you are running is or the code that you're interacting with is the code that it says it is. Yeah, there's two main like threat models. It's very simplified. Side channels. This is more of like information flow control, so trying to leak things out of it. If you're observing someone, say they're running a block builder in a TE, there is like, they're using some type of encrypted storage, but oh, they touch this part of the memory every 12 seconds. Like, okay, that's probably the state tree. They're pulling from this one area every like few hundred milliseconds. That's like probably the transaction pool. There's a lot of ways to mitigate side channels. ORAM is one of the biggest, oblivious RAM. I won't go into that. There's also like physical side channels. So an ion microscope, I honestly would be quite bullish if searchers were required to use an ion microscope in order to exploit these protocols. I think that'd be pretty awesome. Yeah, and then there's also like a memory transposer. It's similar to like a Game Shark or like a Game Genie on Game Boys, if you've ever used those. Yeah, and then the other class is like protocol exploits. So the biggest example of this was Secret Network a few years ago with sgx.fail. There was a vulnerability that was exposed in SGX. The Secret Network was like privately disclosed this. They did not patch it. It was then publicly disclosed, and a team of researchers was able to get an SGX, exploit this vulnerability, and then like demo dumping all the secret information on the network. Cool, and then one other note is that the latest generation of TEs is something called Trust Domain Extensions by Intel. The cool unlock here is that it's actually an entire confidential VM, a virtual machine, as opposed to the previous generation, which was just a confidential process. So the cool unlock here is that you can actually get near native execution. So for things like block building, which are extremely latency sensitive, where like this is very exciting. Okay. So defense in depth, this is like a classic security meme, the Mott and Bailey. The story goes like, there's a town, there's a bunch of people that want to, do their work, farm, raise livestock, etc. But they're also in an area that gets attacked quite often. So what do? They set up their town area, they set up some basic defenses, a wall, a moat. They use that to protect from like small incoming people interested in taking them down. And then when that appears not strong enough for their opponent, they are able to retreat back into the keep, which is on top of this Mott. The core idea is that just like essentially you have layers of your security, and modern computers and infrastructure have like many different layers here. So I think for security, TEs provide defense in depth by giving you isolation of execution. This isolates sensitive computations from the rest of the system, ensuring that even if like the operating system is compromised somehow, the code and data within the TE remain protected. Attestation and verification, as I mentioned before, and then hardware attacks as well. So for privacy, you get confidential data processing, selective data sharing, encrypted data storage. You can mimic a lot of these things with other techniques, but with TEs, you get them out of the box for quite cheap. And then maybe the more controversial claim is that you also get defense in depth for cooperation. So I think in my mental model, like a smart contract sort of gives you some guarantees around like what the logic of the protocol you're interacting with someone is. You can sort of verify the code on chain. Consensus then gives us another layer by agreeing on the execution of public inputs to the smart contract. MPC would be like a next layer where you can do like semi-secure computation over private inputs, and then TE would be an outer layer where you could bootstrap your MPC and like protocol using a TE. So the key takeaway here is that code attestation plus privacy and security features massively limit the adversary attack space in your supply chain. I think one of the hardest problems in permissionless protocol design is that you just like, it's hard to know what what an adversary is doing. Incentives get you like very far, but we've seen attacks where, such as like the Meb Boost exploit with the Low Carb Crusader, where the incentives were large enough that they were still able to attack the protocol, and bugs in the protocol, which are always there. And one thing I didn't mention is that you can see at the bottom here, cheap one-shot signatures. If you've ever heard of this, they sort of rely on quantum cryptography, but the core idea is that a like public key is only, or private key is only ever able to sign one message, which is really cool because a lot of the work done in proof of stake protocols is to basically ensure that a proposer is not attesting to or promoting like two different states of the world. So the TE, you can just have like a very cheap version of this, which is obviously like not theoretically secure, but gets us much closer. Okay, So I'll go into rollup interop now. Hopefully this diagram's pretty self-explanatory. Yeah, so there's two, so this is the Optimism interoperability protocol, as I mentioned. There's two key pieces here. So you have an initiating message and an executing message. And then we have two rollups, rollup A, rollup B, and we're assuming one block builder for both of these chains. So what happens is the user sends a transaction to the mempool. This is seen by the block builder. They then insert it into the rollup A, the pending block on rollup A. This will then emit an event which allows them to then place the executing message into rollup B. I'm glossing over like a bunch of details, but this event that is emitted is able to then be used in the like fraud prover to show whether or not this message was like valid under the protocol rules. Cool. So the message identifier, we'll just go into this really quickly. You can see there's a bunch of fields: origin, block number, log index, timestamp, and chain ID. The one I'm going to focus on is the log index. So the interesting thing here, because fraud proofs need to know a specific spot in the block in order to prove fraud, you can't basically just like arbitrary, you can't create a fraud proof that just like arbitrarily searches through many different blocks. You need to have the log index. And if you're unfamiliar with how block building works or how a block is constructed, there's an index of all the logs that are emitted from transactions. So if you're the first log in the block, you're 0. If you're the last, you're potentially some arbitrary number depending on how many logs were emitted. So the thing that's really tricky about this is if you want synchronous composability, you need to know this log index on chain A before it's included on chain B. So that's fine if you have one block builder. They're constructing blocks for both chains. They obviously know. But what happens if you have two block builders? Then you need to pass this message from block builder A, which is, that opens up a lot of area. Particularly, this is a griefing vector, so what block builder A could do is say they're including the transaction in the first slot. They could then pass that message to block builder B. Block builder B will then include it, but then what happens on the network is block builder A will not actually propose a block with the initiating message inside of it, therefore invalidating block builder B's block. So yeah. That's a trick, or that's a problem that we have to overcome here. What if a block builder gives a log edits? Cool, and now we'll get into preconfs. So yeah, interop grief, what to do? I think we have two options. We could do shared sequencer, as we initially mentioned. There is, this isn't a problem if you're building both the blocks. The next option is preconfs. But this enables cooperation, but you need to trust yourself. I think this meme might be a bit controversial. I am basically just saying there's trade-offs to both approach. I'm not actually saying these are like dystopias. My hot take around this would be that the winner of the sequencing rights auction like most likely won't be a block builder. Block builders are really good at building, or like basically scaling compute, building platforms for expression of different transaction types and providing different services. Unfortunately, some like market structures don't really incentivize new features. They incentivize more like order flow purchasing, but in an ideal world, that is how a block builder should operate. So yeah, I also think like one block builder is unlikely to accommodate all the different block types and VMs and protocol rules associated with different rollups. So that's also like, I think, another argument. Perhaps though we have like some type of like autonomous bidding ring. That's just like a shower thought. Like potentially a bunch of people could just push their order flow somewhere or some programs and like purchase block space in the future. But in the event that doesn't happen, I think we still need preconfs. I think someone will basically buy a block. They will maybe insert their top of block arbitrage, and then they will sell the rest of it off, which they'll probably use through preconfs. So yeah, I think we need to like decompose the block somehow. Preconfs are one of the most popular ways. I think also if you squint, preconfs look very much like a shred in Solana. So I just replaced the message identifier with the shred here. But if we want to get into it a little bit more, like from the Solana spec, basically, shreds are fragments of blocks or transaction data that facilitate propagation within the peer-to-peer network in Solana. And you can do cool things like erasure code them and use like forward error correction, things like that. A super simple spec for like what a shred would look like in Ethereum is you just have the index, the list of transactions that are in this shred. It could be one if you just want this to be a one transaction preconf, and then you got a bunch of other stuff to just sort of like say where in the block you are and where in the chain you are. And additionally, you could add a proof here as well, which is cool. You could do a TE proof. You could do other types of proofs as well. Cool. So I think the other cool thing that happens here is block builders can share these like shreds or preconfs between each other, but they could also just give them to the user. And now this is like what looks much more like a preconf. Yeah, cool. So the key takeaway, we need shreds for interop, and they also give us preconfs. But we didn't really achieve our goal of stopping the grief vector I just described. I think we just like added some more words. So I think one of the key points I want to make here is that if you think back to what I was talking about with the features and functionalities that the preconfs offer, that is code attestation, privacy, and security, which allow us to massively limit the adversary's attack space. So basically, if we run these different sequencers in a TEE, we can be sure that they're using block production rules that enforce the interop protocol response on the sequencer's side. This does not mean we like ignore economics and they will just magically insert all interop messages. This solely means that if a sequencer gets a message from another sequencer in a TEE, it can be much more confident that that sequencer is actually including that message. There's also no staking requirements or accidental slashing in this approach, which is just more capital efficient. Yeah, and then some hot takes to finish this off. I think sync interop doesn't make a ton of sense between like two arbitrary rollups. I think it's more likely it'll be amongst like a federation of rollups that works very closely together. I think this looks a lot like the optimism superchain thesis. And perhaps we'll see some type of like zipper preconf where these different sequencers are passing around preconfs back to each other and building on top of each other. Cool, that's the end of my presentation. We're launching our TDX testnet in 2 weeks as a small plug, and then we'll also be working on the shred spec in public just for fun. Cool, thanks.
You talked about specific advantages of TE, right? Attestation, privacy, security. Is it possible to build rollups directly on top of TE, given that you could potentially have a VM in TE and use them as a way of building rollups instead of just focusing on optimistic and ZK rollups that we've been doing so far?
You definitely could. I think the better approach is like an MFA type of scenario where you use like a ZK proof and a TE proof together, or multiple different proofs, which also gives you defense in depth on your proofs.
What would be the motivation to use both? Why not just TE proofs? Just trying to get your thoughts given.
I mean, we do see that they get exploited about like once a year. They're definitely not perfect technology. So I think it's just good to have multiple different approaches, like in whatever computer system you're working on. There is like one argument that you could say for your consensus protocol. I think there's been a claim that you can like change the Byzantine fault tolerance, basically like threshold to, I think, like omission fault tolerance, which like maybe decreases or increases the amount of the amount of nodes you need to control, but I wouldn't really rely on that as your
just one counter argument. Most of the exploits, as you mentioned, the secret network exploit, all these exploits have been related to privacy, right? But if we're building a non-privacy simple general purpose rollup, that wouldn't need privacy requirements specifically.
Yeah, if you were able to exploit it, you would leak everything, but you could also force in your own transactions. Okay. So,
got it.
Yeah.
Thank you.
All right. Cool. Thanks.
Thank you.